Materials that heal themselves and get stronger on impact. The future is already here. Can a material become stronger after an impact? In science fiction and film, the concept of ultra-durable materials has long become a cliché. For example, Wolverine's claws from the X-Men franchise, fictional blades that slice through metal without sustaining damage. On screen, it looks like stylish fiction. But in recent years, engineering has come close to developing real materials that behave in a similar way. We are now talking about substances that not only withstand impacts, they actually become stronger when struck. Researchers at the Massachusetts Institute of Technology and the University of California have developed a polymer that increases its strength under pressure. Its durability can grow by up to 30%, precisely at the moment of impact or deformation. And this reaction occurs not in minutes, but in fractions of a second. Under normal conditions, the material remains flexible and lightweight. But when hit, its internal structure compacts to resist destruction. This is not an isolated discovery. Research in this area has been ongoing since the 1970s, but only recent advances in nanomaterials, polymer chemistry, and 3D printing have made practical applications possible. Modern prototypes are being tested for flexibility, abrasion resistance, and ballistic durability. You can cut, strike, or drop the material, and it continues to function without losing strength. The principle behind some of these systems was inspired by a familiar substance, starch. When mixed with water, it creates a non-Newtonian fluid. It flows like syrup under slow movement, but hardens instantly under sudden force. This behavior became the model for materials that respond to threat, not by breaking, but by tightening up. This new class of materials opens up the possibility of adaptive armor, smart coatings, and structural components that don't just passively resist damage, they actively respond to it. This is no longer science fiction. It's applied science entering real-world deployment. How do self-healing materials work? These materials rely on various physical and chemical mechanisms. At the core of most are long polymer chains and reversible bonds that can break and reconnect. Imagine a tangled network, like prayer beads or spaghetti, where the strands are connected by movable joints. When stress is applied, some of these connections break. But under the influence of heat, light, or other triggers, they reform. This is the essence of self-repair, not just holding shape, but actively fixing damage. Many polymers use heat-activated bonds. When heated, molecular segments become mobile and migrate toward each other at the damaged site. Using diffusion and self-assembly, they literally zip the material back together. Some plastics can do this at human body temperature, around 37 degrees Celsius. Lab versions already heal in 10 to 30 seconds and survive up to 100 damage cycles. Metals follow a different logic. In materials like copper and titanium, impact triggers ballistic transport of dislocations, shifts in the atomic structure that compact and strengthen the material locally. Instead of cracking, the internal lattice becomes denser, as if the metal remembers the blow and reinforces itself. There are also capsule-based systems, especially in concrete, ceramics, and composites. Tiny capsules embedded in the material burst when damaged, releasing a healing compound that solidifies on contact with air or moisture. One drawback is that these capsules are single-use. Once burst, they must be replaced for further healing. Another approach uses embedded microchannels, similar to blood vessels, that distribute healing agents. This method is used in smart composites that direct repair fluids precisely to the area of damage. Some materials respond to ultraviolet light, such as coatings that heal scratches when exposed to sunlight. This technology is already being tested in smartphones, building facades, and protective films. All these systems are united by one principle: damage is no longer the end. It's a signal to respond. The material is no longer passive, it adapts and repairs itself. Where are these materials used today? Self-healing materials are no longer experimental. They're already in use across construction, medicine, aerospace, and defense. Their core value is not invincibility, but the ability to maintain integrity after damage without human intervention. One of the best-known examples is self-healing concrete. It contains either bacillus bacteria, which produce calcite to seal cracks, or capsules filled with minerals that do the same job. Such materials are used in bridges, tunnels, support structures, and buildings in earthquake-prone regions. The benefit is reduced maintenance and longer structural life, especially critical for urban infrastructure. Self-healing polymers are used in coatings, smartphone cases, cars, and helmets. They repair small scratches using warmth from human touch or sunlight. Some lab-grade plastics can do this in seconds, repeatedly up to 100 cycles. In aviation and military technology, smart composites with sensors, channels, and repair agents are being deployed. They deliver healing compounds to microcracks like a vascular system. This is vital in components where invisible cracks could cause critical failures. Self-healing ceramics are used in high-temperature components, such as turbine linings and rocket casings. Damage bursts internal capsules, releasing compounds that fill and seal the cracks. These materials tolerate extreme heat and pressure changes. Metals with adaptive hardness are used in body armor and drone casings. They don't deform, they stiffen, allowing machines to keep operating after impact. In medicine, regenerative polymers and hydrogels are used in prosthetics, implants, and artificial skin. They can close micro-injuries and burns, gradually restoring the affected area. Even tires can be made self-healing. Rubber filled with microcapsules seals punctures, and disulfide bonds restore the original shape. These materials don't make systems indestructible, but they slow damage progression, extend service life, and reduce failure risks, which saves money and preserves functionality in critical environments. How much do these materials cost, and when will they become the norm? One reason these materials are moving from labs to the real world is cost efficiency. At first glance, self-healing concrete is around 30% more expensive than standard types. But it greatly reduces long-term repair and maintenance costs, especially in difficult-to-access locations like tunnels, bridges, or skyscrapers. Self-healing polymers average up to $15 per kilogram. Medical-grade materials up to $100. But mass production and 3D printing continue to drive prices down. According to engineers, these technologies pay off in about 5 years. This makes them attractive for infrastructure, defense, transport, and electronics. By the year 2030, self-healing materials may become the default standard, not the exception. They're already used in armor, helmets, drones, and aerospace coatings. Not to make systems indestructible, but to keep them functional longer and avoid critical breakdowns. This marks a shift in engineering thinking. Strength is no longer just about resisting damage, but about responding to it. Not rigidity, but adaptability is becoming the new definition of resilience.